The utilisation of low-carbon hydrogen is one of the major strategies outlined by the UK government in the stride to reach net zero by 2050. Lightweighting of hydrogen pressure vessels utilising composites aligns with the AMRC's hydrogen propulsion strategy. The AMRC Composite Centre has conducted a lot of work in the development of composite pressure vessels to help de-risk, industrialise and scale up the manufacture of these vessels to develop and support the emerging UK supply chain.
For design optimization of pressure vessels, we are currently making use of theoretical methods to generate the composite layups for programming into the filament winding softwares, followed by computational mechanics simulation to assess the structural performance of the tanks. Currently working on a step-by-step validation process by manufacturing and testing 100 bar, 200 bar and 350 bar pressure vessel tanks. Our aim is to achieve a low-cost and low-weight solutions for hydrogen storage pressure vessels.
At the AMRC, we have a state-of-the-art high-tension filament winding system, which we use to manufacture pressure vessels, as well as a diverse range of other components. We start the manufacturing process by programming the part using various filament winding software, including Composite and CAD-Fill. We take the final layup generated in the design phase and make minor adjustments to optimise the winding process. During the winding process, we can monitor the live data on the system's HMI, and that data is then stored so that we can review it retrospectively and use it to improve the process. We recently used this to find the optimum robot speeds for a range of winding angles, whilst ensuring that the tension remained constant, which can be difficult when complex motions are conducted at high speeds. The finished vessels are then typically cured using our large Caltherm oven to finish the process.
For material and structural testing, we have in-house testing capabilities that we can use to characterize and analyze the vessels that we manufacture here at the AMRC. So this includes a range of characterization equipment that we can use to calculate the void content and fiber volume fractions from various samples. AMRC testing labs have acquired high-pressure testing capabilities that can test up to 2,700 bar. So we can perform both burst and fatigue testing in accordance with the European EC 79 standard.
The AMRC has also collaborated with Haydale Composite Solutions on the Innovate programme Reach Out, developing graphene-enhanced Thermoset composite materials ideally suited to Type 5 pressure vessels, whereby the graphene enhancement reduced the permeation of hydrogen. These materials could be applicable for all pressure vessel types incorporating composites.
One current disadvantage with standalone filament winding is that cylindrical sections end up with more material than necessary to ensure adequate dome strength. To try to overcome this, Boeing and Civitec have used AFP and FPP respectively to first reinforce liner domes prior to overwinding, reporting mass savings of 32% and 15% and cost savings of 20% and 15% versus conventionally wound vessels. The AMRC is developing another route that we believe will trump these approaches overall. Watch this space. The lightweighting here and use of less material of course relates to sustainability, which is a core AMRC strategy. We're additionally researching new methods of recycling Thermoset composites and reusing thermoplastics to reduce the overall environmental impact of making hydrogen pressure vessels from these materials and to accelerate net zero ambitions.